Hello and welcome everyone to our webinar that's offered jointly by the Mobilize Center and Restore Center at Stanford University. My name is Matt Petrucci. I'm the Scientific Program Manager at both these centers, and I'm excited to be your moderator today. Today's speaker is Melissa Boswell, who will be presenting Sit2Stand, which is a software tool for capturing and automatically analyzing self-collected at-home videos of the 5-repetition Sit2Stand test. The first part of the webinar will cover the research study results, motion capture validation, and translation of the tool into an ongoing decentralized clinical trial. In the second part, she will share how to use the Sit2Stand tool for your own data collection, implement their processing and analysis pipelines, and she will conclude with best practices and pitfalls of conducting large-scale digital studies. Today's webinar is brought to you by the Mobilize Center and Restore Center, which are both supported by the National Institutes of Health. The Mobilize Center is focused on developing and disseminating state-of-the-art biomechanics and machine learning tools for researchers to analyze human movement. The Restore Center is working to make these and other tools for real-world assessment of movement more widely available to the rehab research community. Before we get started, a couple of quick reminders about the format of the webinar. We will have a research talk and then a tutorial, and we'd love to take your questions from both. So we'll take your questions at the end of the research talk and at the end of the tutorial session. Please type your questions into the Q&A panel in Zoom, so not the chat, and we'll review them from there. Now I'd like to introduce today's speaker. Dr. Melissa Boswell is a postdoctoral scholar in bioengineering at Stanford University. She is passionate about measuring mobility as a biomarker, motivating movement, and increasing access to healthcare through data-driven digital tools. Her research bridges advancements across bioengineering, psychology, and computer science to understand and tackle significant problems in human health. She values human-centered design and a holistic, lifestyle-focused approach to engineering and medicine. She also enjoys cultivating creativity and humor in work and life, sharing her ideas and entrepreneurship, communicating science, particularly on her podcast, Biomechanics on Her Mind. Dr. Boswell received her PhD from Stanford University, where she developed and deployed tools for large-scale access to biomechanical assessments. She received several awards for her PhD work, including the NSF GRFP Fellowship, the Gerald J. Lieberman Fellowship, and the World Congress of Biomechanics Young Researcher Award. With that, we're excited to have you all here today. I know we're all excited to hear Melissa speak about this amazing tool, so I'll let her go ahead and begin.
All right, thanks so much. I'll go ahead and share my screen. How is that?
Looks great.
Okay, fantastic. Oops. There we go. Okay, great. Well, I'm really excited to be here today. Thank you for the great introduction, Matt, and thank you all for joining me today. I'm excited to share some of my research on an at-home sit-to-stand test and how we deployed that in a nationwide study, as well as how to implement that in your own studies, which I hope will be useful for your research moving forward. And I'm excited to get your feedback on that, as well as your questions. So I'll go ahead and start on the motivation, the scientific findings, and the translation of this work into a decentralized clinical trial. So as many of us know, assessing one's biomechanics can help us to identify, understand, and design treatments for diseases and disorders that affect movement. One movement that is particularly indicative of one's physical health status is the sit-to-stand transition. And sit-to-stand transition tests are widely used in clinics to test physical function by measuring the time it takes to complete the test with a stopwatch. However, movement is a key determinant of sit-to-stand strategies. And in fact, kinematics of the sit-to-stand test, so things like joint angle ranges and velocities, are related to a number of health factors, including frailty, age, and osteoarthritis. So while the timing of a sit-to-stand transition is indicative of physical function, this can be influenced by a wide ranges of diseases, injuries, or demographics like age. But kinematics can give an additional insights above timing alone that are more sensitive and to certain conditions that really can't be captured with the stopwatch that's used in the clinical settings. However, biomechanical assessments have traditionally been limited to laboratories with expensive and technical equipment that aren't easily scalable or accessible in a clinic or at-home setting. In recent years, though, there has been tremendous growth in tools that enable biomechanical measurements outside of the lab. So things like inertial measurement units, wireless electromyographic sensors, shoes instrumented with pressure sensors, as well as pose estimation algorithms that predict the location of joints from 2D video. And this motion analysis from 2D video is a particularly exciting opportunity as 83% of the global population owns a smartphone and could access their own pocket-sized tool for quantitatively self-assessing movement. So these algorithms, such as OpenPose shown here, can detect poses from videos outside of the lab. Specifically, they detect what we call key points, which are the positions of specific anatomical landmarks. And on average, you can see here it is fairly accurate, but is it accurate enough for medical applications? And this is really what we sought to answer in our study. Due to its clinical relevance, we chose to focus on the most common variation of the sit-to-stand test in our study, which is the 5-repetition sit-to-stand test, where an individual goes from sitting to standing 5 times as fast as possible with their arms crossed in front of them. During the study, participants collected a video of their sit-to-stand test at home using a smartphone, and we asked individuals to have another person record this test for them, mainly for their safety, and we asked that they stood at a 45-degree angle to capture both the frontal and sagittal planes, as well as stand about 5 to 10 feet away from them, making sure to have their whole body in the camera frame. The video is then uploaded to the cloud, and a pose estimation algorithm detected the joint locations or the key points in each frame throughout the movement. We did some additional data cleaning and processing on the results of these out-of-the-box algorithms, which I'll share now. So we use the software from the Fast Forward Moving Picture Experts Group, or FFmpeg, for extracting frames. And then we used OpenPose as our pose estimation algorithm. And if you stick around for part 2, I'll share how you can actually use other pose estimation algorithms. While we instructed the recorder to record to the right of the participant for consistency, we horizontally mirrored key points in cases where the participant's left side was closest to the camera. To have everyone on the same scale and with the same center of the coordinate system, we used the toes of the right foot as a center of the coordinate system. We normalized to the 95th percentile of the distance between the right angle and the nose, which is approximated as the participant's height in pixels. And then we observed high frequency, low magnitude noise in the OpenPose output, possibly due to the low resolution of the input, just as the at-home videos for the OpenPose neural network. So we applied a low pass 6 Hertz Butterworth filter, which was the most robust compared to spline smoothing or Gaussian smoothing. And then in frames where the algorithm detected multiple people, we only considered the person closest to the camera, defined as the detection with the greatest distance between the feet and the nose. And finally, we use linear interpolation to estimate missing key points positions in a given frame. We then computed the key transitions of when the participant rises from the chair and returns to sitting. We did this by using the nose marker's local peaks in the vertical axis. In addition to time to complete the task, we computed biomechanical parameters, which I'll explain in more detail shortly. Before launching the study, we wanted to validate our video-based sit-to-stand parameters to laboratory measurements for marker-based motion capture. So to do this, we collected sit-to-stand data from 11 healthy adults and had them perform sit-to-stand in a variety of ways. We measured gold standard kinematics with an 8-camera motion capture system. We used OpenSim 4.0, which is a musculoskeletal modeling software, to estimate joint kinematics from marker trajectories. We first scaled this musculoskeletal model to each participant's anthropometry based on anatomical marker locations from a standing calibration trial using OpenSim's scale tool. And then joint kinematics were computed using OpenSim's inverse kinematics tool. Similar to our at-home setup, we used phone cameras at a 45-degree angle for the in-lab video-based assessment with the same processing pipeline as I explained earlier. We computed the time to complete the sit-to-stand test using motion capture and OpenPose. Since the nose marker was not collected in motion capture trials, although that probably would have been fun to do. For comparability, we used the peaks of the pelvic markers in both settings. And then we defined the sit-to-stand phase as the time between local minimum and the following local maximum, and the stand to sit phase as the time between a local maximum and the following local minimum. And we calculated the total test time as the time between the first sitting position and the last standing position. In our manuscript, we focused on trunk kinematics. So we did this in our validation as well. For trunk angle and trunk acceleration, video-based kinematic measures were calculated in the camera projection plane as the angle between the vertical of the camera frame to the line connecting the right hip and the neck key points. And you'll see the results of the manuscript. For these results, the angle was with the vertical pointing down as it shows here. But to compare to motion capture, we subtracted 180 degrees. So it was typically an angle between 0 and 90 degrees. To compute marker speeds and joint angular velocities and accelerations, we used discrete derivatives and divided them by the frame rate. And then we averaged the total test metrics across the 5 sit-to-stand cycles. And we compared these measures to the most similar motion capture-based parameters. So for trunk angle, we combined lumbar flexion and bending to get kinematics from both planes, as we do from a 45-degree angle. And then for trunk acceleration, we used lumbar flexion acceleration. To compare our video-based measurements to motion capture, we used R statistic, or the square root of the coefficient of determination R squared. And the R of the total time between the two settings was 0.997. So we found a strong correlation there between motion capture-based time and video-based time. And previous studies have found that using motion capture or IMUs to capture sit-to-stand times has not only higher accuracy, but also higher predictive power than stopwatch-based time. So it was really great to see that our video-based pipeline is on par with motion capture. And then we found moderate to strong associations between sit-to-stand parameters extracted from our web application and from these analogs from motion capture for motion maximum trunk flexion and trunk acceleration. So I wanted to share what the app or what a web app looks like from the user side. So a user would go to our website, sit2stand.ai, and they could from there join our study. They would complete a set of qualifying questions as well as performed digital consent online asynchronously, and then from the researcher, and then they would get the sit-to-stand test instructions, both written and video instructions. And then after recording the test, they would record it, upload it through our platform, and then were immediately directed to a health survey. So close to 500 individuals completed the study entirely self-guided across 35 US states, which was over 35 times the median number of subjects in traditional biomechanics studies in just a couple of months, with very minimal researcher time and resources required. Because of the accessibility of the study, we were able to collect a fairly diverse sample. So in the 405 participants used in the final analysis, the age of participants ranged from 18 all the way to almost 100 years of age. We had a range of BMIs from underweight to obese, about an even distribution of sexes, as well as a range of different ethnicities and races. And here you can see the many different videos that we collected from across the country. And it was really amazing to see so many people able to participate from their living rooms or kitchens and even outside. And from these videos, we get a glimpse into the many different ways people perform the test, and I'll zoom in on a few examples of these different movement strategies. So first, you can see here, this participant goes from sitting to standing fairly easily and with control. And we can contrast that to a participant here who creates momentum to stand up by leaning forward. They have knee osteoarthritis, which I'll share more about. And here's a participant who also leans forward, but it seems like they do so to optimize for speed rather than to minimize the lower body strength needed. And then finally, here's a participant with a movement pattern that falls somewhere between these other strategies. So I first compared the results of the study to the results of past in-lab studies. And similarly, I found longer times to complete the 5-repetition sit-to-stand test were associated with an older age, which is shown on the plot here on the right. Longer times to complete the test were also associated with a higher BMI and lower reported physical health. Larger maximum trunk flexion when going from sitting to standing was associated with the diagnosis of knee or hip osteoarthritis, and this remains significant even when controlling for age, sex, BMI, and test time. It was also associated with increased age. And this relationship between trunk flexion and osteoarthritis indicates that the kinematics we obtain from video may give additional information about health and functioning or particular diseases than just timing alone. Larger trunk flexion among those with osteoarthritis also makes sense from a biomechanical perspective. So you can see here, compared to a typical sit-to-stand test, which is shown on the left, with a larger trunk lean on the right, the knee joint is closer to the ground reaction force, and the knee joint moment is thus reduced. With a link segment model, like the one shown here, studies have found that a 20-degree increase in trunk flexion reduces the knee joint moment by about 30%. Our large and diverse participant pool enabled exploratory investigation in different study population subgroups. And in one such analysis, we found trunk flexion angle differed across racial and ethnic groups, which you can see here. Because two of these groups were non-parametric, shown here are the results from a Kruskal-Wallis test and a post-hoc Dunn's test. But we found that when comparing the two groups with the largest amount of participants, again, these findings remain significant even when controlling for sex, BMI, and age. There have been very few studies examining differences in biomechanics across races, and these findings are hypothesis generating, and more studies need to be carried out to better understand these differences. But it is clear that we can't assume similarity between different racial groups, and future studies really need to make racially diverse study samples a priority. In individuals 50 years of age and older, greater trunk acceleration was associated with higher mental health. And these findings are also hypothesis generating, but it is exciting to see that there may be relationships between mental health and the way that we move. And perhaps movement can complement biological markers in understanding and predicting mood disorders and cognitive performance. And again, assessing mental health or psychological variables requires a large number of people to power them. And similar to having more racially diverse samples, like this just really hasn't happened in traditional biomechanics studies before. So I'm really excited for the ability of these digital biomechanical studies to be able to answer questions we haven't been able to answer before, as well as really be able to access underserved populations. So while it was exciting to see all the places and ways that people perform this test, this inconsistency was also perhaps the most significant limitation of the study. For example, participants used different chairs and the camera angle varied. And in our study, we did ask for participant feedback, which I'll share a little bit more about in the second part. And I think that this feedback in combination with experts in human-computer interaction and design can really make digital tools more precise, more accessible, and more dynamic. And again, I will share more about that next. But I wanted to share that in addition to the publication of this work, which came out a couple months ago in Nature Digital Medicine, our simple web page is available where videos of the sit-to-stand test can be uploaded and timing and biomechanical parameters are calculated and output. So hopefully our pipeline can be plugged into other studies, and I'll talk about how this can be used for both single assessments and for larger research projects in the next part of the webinar. We also released the open source de-identified data set of videos with matching survey measures, including measures I didn't share today. And then all of our code for the website data processing and analyses are freely available on GitHub. So our study was cross-sectional, but I am really excited to also share that we're currently collecting longitudinal data in an ongoing clinical trial, which investigates a digital psychology intervention for people with knee osteoarthritis, which will hopefully improve pain and physical activity levels. We designed the study so that participants will do the at-home sit-to-stand test at baseline and then at 1 month follow-up after the intervention, where we can explore potential changes as well as the association with changes in measures like osteoarthritis symptoms and physical activity levels. And I'm doing this by taking our video and written instructions and just embedding them into the survey platform Qualtrics, which is the main platform for the study and digital intervention. And individuals upload the videos in that platform, and then I download them and can run them through our website or with the Python notebooks, which I'll share about next. And other researchers that I am collaborating with, including a group called the Women's Health Initiative, are taking a similar approach to assess other functional parameters like balance. And so we're really excited to see these longitudinal assessments performed. And I want to conclude with my vision to deploy at-home tools to quantify biomechanics as a marker of health over one's lifetime. So with these tools, for example, we may be able to detect ACL injury risk, recommend specific strengthening programs, detect osteoarthritis, and even prescribe personalized gait modifications or interventions, and warn individuals at risk for falling. And in this way, we can really apply biomechanics in the real world to help people move better and safer and leverage biomechanical measures as a new biomarker of health. So I want to thank all of my co-authors, especially Łukasz Kaczynski, as well as my lab for their support. And thank you to the participants for making the work possible, as well as my funding sources. And I'm really happy to answer any questions now, and happy to also take feedback, and excited for the discussion.
Great. Awesome. Thank you, Melissa, for the super clear talk. We'll go ahead and start the Q&A session. So again, if you have any questions, go ahead and type them into the Q&A panel, not the chat, and we'll review as many as we can before switching over to the tutorial. We'll try to take about 10 minutes. We'll probably start the tutorial around 9:30. So let's go ahead and take a look at some of the questions that have come in. First one is from Samuel Acuna. Are there any HIPAA concerns with uploading videos to the cloud algorithms? I'm not sure my university would allow this.
Yeah, great question. So we use Amazon Web Services, which was HIPAA compliant and was approved from our ethics board. So it would need to be written into your IRB and get approval. In addition to sharing, for us to share the videos too, we did anonymize them with face blurring. So that could also be an option if you wanted to anonymize them first and then process them. And we're seeing that this pose estimation algorithm still perform pretty well after anonymizing them. You can also download the code to your computer locally. So you wouldn't necessarily need to upload them through our platform.
Yeah. Great. It's a similar question from Slavik Dasgupta. He's interested in is Sit2Stand AI still available, which you did mention it's up. In terms of uploading videos from, say, other countries, say Japan, or are there any restrictions on using the tool?
Yeah, that's a great question. Again, I think that would be sort of IRB dependent where you are located. For our study, we only got approval from the United States because you have to get approval from each individual country. But if you are able to do that in your country, I think you will be able to overcome that hurdle.
Yeah, for sure. Another question from Daphne Raz. Were participants instructed to only upload successful trials, or are there any interesting failure examples in the data set?
Yeah, that's a great question. And I do, in the second part, go into some of the failure examples. We allow them to upload any video at this point. I think in the future, and I've actually been working with a team who's developing a web app that to make sure that their full body is in frame, it's at the right angle, and that sort of thing. So I think it's great to start developing some of these fail-safes before video upload. But yeah, there were, like I mentioned, there was 405 videos out of about 500 used for analysis, which 80% of the videos being usable actually seemed pretty good. But yeah, there were things like obstructions, things blocking participants, their full body not in view, which is probably the most common, as well as either recording from like the frontal or sagittal plane entirely. So some of those things we had to remove manually. Again, hopefully we can do that more automated in the future.
Okay, great. Another question from Roos Duen. Thank you for the great talk. I'm curious if it's feasible to integrate external reaction forces like armrest reaction forces into a pose estimation software. The research focuses on investigating the dynamics of elbow load, particularly when performing the task from standing up from a chair. And currently they're using a marker-based system and force transducers. Also, they're a fan of Boom.
Okay, great. Well, thank you for saying that. Thanks for sharing. That sounds like exciting work. So the way our pipeline is set up right now, we don't have it set up to be able to include like those additional forces, but I could imagine that from our pipeline, you could get joint kinematics and build out like a biomechanical model where then you could use some of those additional forces, or the way an individual is starting their sit-to-stand test, to be able to then model some and estimate like internal loads or muscle activations.
Another one from Reginald Fukuchi. Any recommendations related to clothing and background color during the recording?
Yeah, good question. So we did in the instruction video, we asked participants to not wear loose fitted clothing, and to not have like mirrors in the background or other people or animals in the background. Not everyone follows that, but obviously the algorithms do the best with that. I think one of the biggest things we noticed was that individuals who would wear skirts or dresses, the algorithm would not perform as well with, as well as individuals with a higher BMI. And I think this, is likely due to the data that the models are trained on. But I am optimistic that in the future we can take like these massive data sets that we're collecting that are more in the wild. They have a lot more noise and variability and things like background and what people are wearing, and then train more robust models that can be more generalizable.
Definitely. Well, another question from Savik Dasgupta. Is this tool also useful for fall prediction and successful prevention of falls? Have you found any useful associations between your kinematics or other parameters with prospective, retrospective falls in the subjects?
Yeah, so great question. We did collect fall history from participants, as well as fear of falling, which is a psychological variable that's related to potential or that's related to fall risk. We have not done further analyses in that, but since all the data is available, it is open for other people to perform those types of investigations. And then, as I mentioned before, the Women's Health Initiative is actually working on a balance intervention. So I'm excited that they'll be collecting the sit-to-stand test as well as some other tests at home. And we'll hopefully be able to do further analyses on things like balance and fall risk. I think in-lab studies have shown that. So I think I'm optimistic that there will be some signal there from the videos to predict fall risk, but we haven't done that yet.
Maybe we can take one more before the tutorial starts. So another question from Asula Al-Fahad. How deep did the subject, or should the subject sit into the chair? Meaning how far should the knees be from the edge of the base of the chair? They notice that the closer they sit on the edge of the base, it may change the kinematics a little bit.
Yeah, that's a great question. And in-lab studies have shown that the effect of chair height and how an individual is sitting on the chair does affect their timing and their kinematics as well. In our study, we did not restrict that or advise participants on how to do that. So I think that noise that's created from that, we were able to overcome that by our large sample size. But for example, if we want to do follow-up assessments with individuals, they may want to be consistent in that. And I think that's something to consider in future assessments. But I do think it's interesting too, to be able to learn from videos that are more unconstrained and in the wild, and then can perhaps, design better ways to take these measurements as well.